Introduction into the overall IoT security architecture, and it highlights 6 key principles, as explained by George Cora, the CEO of an IoT security company. Developing secure end-to-end IoT solutions involve multiple levels from end to end: device, communications, cloud, and lifecycle management. First layer, secure device layer or endpoint security. It refers to the hardware level of the IoT solution. ODMs and OEMs who design and produce devices are increasingly integrating more security features in both their hardware and software, which is running on the device, to enhance the level of security on the device layer. Important features include chip security provided by some manufacturers that can act as a root of trust by protecting sensitive information and credentials. Secure booting, used to ensure only verified software will run on the device. Physical security protection, to guard against tampering if an intruder gains physical access to the device. IoT security architecture principles on the devices include device intelligence. Effective and secure connectivity must be powered by smart device. Edge processing means that these smart devices can process data locally before it is sent to the cloud. Second layer, secure communication layer or connection security. This refers to the connectivity networks of the IoT solutions. When sensitive data is transmitted, unsecure communication channels can be susceptible to intrusions, such as man-in-middle attacks. Important IoT security features at this level include data-centric security solutions, ensure data is safely encrypted while in transit and at rest. Firewall and intrusion prevention systems, designed to examine specific traffic flows terminating at the device, to detect unwanted intrusions and prevent malicious activities on the communication layer. IoT security architecture principles at the communication layers include initiate a connection to the cloud and not in the reverse. The inherent security of a message. Each message can be handled according to the appropriate security policy. The third layer, secure cloud or cloud security. This refers to the software backend of the IoT solution, such as where data from devices is ingested, analyzed, and interpreted at a scale to generate insights and perform actions. So the important IoT cybersecurity features at this layer include sensitive information stored in the cloud. That's the data at rest, must be encrypted. Verify the integrity of other cloud platforms or third-party applications to protect against malicious activity. Digital certificates can play a key role for identification and authentication. Fourth layer, secure lifecycle management layer. This refers to an overarching layer with continuous process required to keep the security of an IoT solution up to date. Include ensuring sufficient security levels are in place from device manufacture, initial installation, to the disposal of things. Security by design is only the first step in ongoing effort to keep an IoT solution secure. Further steps throughout the lifecycle include policy enforcement, regular auditing, and vendor control. Hurdles securing the IoT. There's no consistent or official software update process or mechanism. There's a little or no understanding of the cyber threats embedded in their system. There's a lack of accountability for device security. Improper configuration or purpose-built features that equate to security flaws. Data privacy. Practical IoT security assessment. Define system scope for assessment. Understand designs and technical capabilities of device component, communication protocols, and the end-to-end system. Model threats and resilience expectations. At device level, data storage, firmware, connection levels, and system levels. Model traffic flow and trust boundaries. On device, device to system, and system data functionality. Assess. Review configuration, standard application, product assessments, debug, and vulnerability test. Code review. Securing the IoT. Keep your software, firmware updated. Ensure that connectivity is secure. For example, two-factor authentication. Secure the location of data being reported by an IoT-linked devices. Ensure supply chain security. Prevention of counterfeit hardware by procedures to certify manufacturer's supply chain process to prevent the introduction of malicious code. Support IoT security. We must support regulation that requires that IoT devices meet security standards, just as we require standards for our own electrical devices with user-level approval requirements. Use out-of-band OOB systems, closed systems like intranets that are not open to the public. The Defense Department uses IoT-linked devices, but they are mainly out of reach from hackers because they are OOB. Defense weapon system and even sensor-wearing soldiers report critical status information to centralized control entries that feed decision makers. We are less vulnerable to being hacked. These OOB systems are subject to insider attacks. Stay informed. National Institute of Standards and Technology, NIST, and federal guidance such as Federal Information Processing Standard, FIPS, address critical steps that are needed to secure and protect information and critical systems.